Hello, and welcome to a digital lecture for Calculus 2 at Salt Lake Community College. In this video, we're going to go through section 12.2, which has to do with vectors. We talked a lot about three-dimensional concepts in the last time, and we are going to come back to three dimensions in just a moment, but we want to first discuss the concepts of vectors, and then we're going to relate to what vectors are going to be in both 2 dimensions and also 3 dimensions. A vector overall is trying to show two different things. It's trying to show a magnitude and a direction of something. Usually you can consider a vector to be like a force. For example, if you're pushing on a box, the vector could be you pushing on the box. There's also another vector that is the drag or the friction of the box on the table or whatever it's sitting on. Another vector could be gravity. There's also something called a normal vector, or the normal force. There's a lot of these forces that each have a magnitude of how much you're putting into it and in what direction they're traveling. So 2 different pieces of information. Those vectors will all begin at some initial point and will go towards some terminal point. And we always designate that to look like a ray. So something like 1 point here and then a ray over to a new point. The ray part of it is important because that will help us indicate which is the initial point and what is the terminal point, where we're beginning and where we're ending. Usually, a lot of the variables we tend to use for vectors are v, u, and w. Those are the most common ones, particularly if we have 3. For the time being, I will very often be using v and w to denote vectors. And that's simply because the book does a lot of V and U, and it's very hard to distinguish between V and U when writing them quickly. I think it's a lot easier to do V and W and indicate which one is which. However, just note that those are very common vector symbols, just like X, Y, and Z are used to denote coordinates in the three-dimensional system. Now, a vector is written in a few different ways. You either have the label for the vector, the variable we use for it. We have a way of indicating both the initial and terminal point, so A to B with an arrow indicating the direction, or you have what is called component form. Component form is where you indicate both the X and Y, and if you're in 3 dimensions, the Z coordinate. And those are going to be real values. Note that we indicate the parentheses instead of a round parentheses like a coordinate, we indicate these angled brackets. So angle V1, V2, and then if you have 3 coordinates, V3. This would be the component form. These 3 components are going to indicate to what X, Y, and possibly Z coordinate the vector is going to go towards if that vector were to have an initial point at 0. However, vectors can really begin anywhere. Whatever the component form is, we could have that vector starting at any given point and going that much in the X direction, that much in the Y direction, that much in the Z direction. If we do indicate a vector starting at the origin, we say that that is in standard position, which is usually the easiest way to work with them. Now, when talking about these vectors, what we also want to do is talk about the different algebra we can do with the vectors. For example, the first thing we're going to talk about is how to deal with addition between vectors. So the sum of 2 of them. I'm going to say the sum of 2 vectors, v and w. The best way to indicate direct addition of vectors is to start with one vector and then have that go to a terminal point and then indicate the other vector beginning at that same terminal point. So, for example, if I have v that goes in this direction, this is v, it goes from this point to this point. And then I have W that goes like this. Indicate V plus W is by taking V, starting from some terminal point, V, and then indicating W starting from that terminal point out. The line in between those, which I'll indicate with red, the line in between those from the initial point of V to the terminal point of W, this would indicate V plus W. Note that you could also do the other way around. If I start at that same point, but I start with the W vector instead, well then W would expand out this direction. And then from the terminal point of W, I then work with the vector V. V is going in this direction to that same point. So I still have V plus W or W plus B, V represented in the same way. If you have both the vectors starting at the same point, for example, I have W coming out like this, and I have V coming out in this direction, V and W, note that looks exactly like the parallelogram in the previous case, and we could say that V plus W expands out from that. So V plus W is going to come out of that area, or out of that region. This is overall how you would designate an addition of two vectors. The easiest way is by just lining them up using initial and terminal points in succession. But if you need to put them on the same place, you can imagine V plus W comes out in between those two vectors. Overall, the components of the vectors follow as like we have right here. You take V plus W, which is going to take the components of V plus the components of W, and what you're going to get is a new vector. Note that we got a new vector V plus W in red, and that new vector is defined by the X components added together and the Y components added together. That's how we do vector addition. So we've shown how to do it graphically and how to do it with calculations. However, because we've shown the algebraic way of manipulating, we also need to be able to verify whether this addition operation we've defined between vectors is validated. Because we talk about addition between numbers, we talk about addition between algebraic values like 1 and 2. I could do addition of that, and that's been verified and defined beforehand. But vectors are two completely different things. It's like adding two boxes together and getting a new result. So we need to talk about what that addition means, or what this operation means, vector addition specifically, and make sure it is what is called closed. To close any property to close any operation you have, there's a few different properties you want to work with. First, you have the commutative property, which means A with that operation, I'm going to use that circle with a dot to indicate any operation, is going to be equal to those same variables just flipped. So A dot B equals B dot A. Same thing with the associative property you may be familiar with. If you associate two values together and then you do another operation on that, that's the same as doing the last two values and then the operation of the first. You can associate it in any direction possible. And lastly, there's also what is called the identity for that operation. The identity is some value I, such that when you operate with that, you get the same thing back. These are all operations or identities and properties that you've shown before for other concepts. For example, A plus B and B plus A. These are all things we already know. Commutative associative property we know. And stuff for the addition, for normal addition, for addition of values, if you do A plus 0, that gives you A. That would be the identity for addition. Likewise, for multiplication, A times B equals B times A. And we also have, for the identity of multiplication, is 1. That's called the multiplicative identity. You can multiply anything by 1, you get the same thing back. These are all things that have been established before in algebraic courses for other operations, and we need to also establish it for this new operation, for vector addition. Thankfully, doing so isn't really that bad, and the reason why it's not that bad is because the way that we actually operate is with the algebraic values on the inside. So verifying commutative and associative properties is relatively simple. Here, if we have A as a vector, or let's see, V is V1 and V2. You can expand this to 3 dimensions as well. And W is W1 and W2. We want to make sure that V plus W equals W plus V. Well, when we do that, V plus W is going to give me V1 plus W1, and then V2 plus W2. That's what that addition means. And then if I do the other way around, W plus V, I get W1 plus V1, and then W2 plus V2. This we verify as true because the inside, we know that V1 plus W1 equals W1 plus V1 by the commutative property of addition. We know this is true for algebraic values. So since that's true for algebraic values, we can expand that back and say that's also true for these vector values. So that's the commutative property. How about the associative one? That one's a little bit more complex, but we could still analyze that by looking at the components. If you have VW, and we also say U is U1 and U2, then we can say V plus W plus U equals V plus W plus U. And we just need to show that. V plus W, we already know, is V1 plus W1, and then V2 plus W2 plus U. And on this side, we have V plus W plus U will give you W1 plus U1, and then W2 plus U2. And now, when we add U to the left-hand side and V to the right-hand side, we get V1 plus W1 plus U1, and then also V2 plus W2 plus U2 equals the other side of, because we start with V, which is V1 and V2, we get V1 plus W1 plus U1, and then V2 plus W2 plus U2. So that means that's checked, because this equals that, we're all good. So that's the commutative property. Just making sure one side equals the other. And lastly, we need to identify an identity. We need to identify a value such that if we operate with that, it doesn't change the number, or the thing we're working with. In this case, if I take V, I want to find something that if I add to that, I get V back. Note that it's not going to be the same as the addition identity, which is 0. Like 3 plus 0 is still 3. We're talking about a vector here, and we can't add a vector and a constant, or what we'll call a scalar in just a moment. This we cannot do. But what we can do is take a vector and add another vector that has components of 0. That will still equal V. We say the 0 vector is the identity. A 0 vector, or 0, 0, is the identity, such that if I were to add that to anything, it doesn't change the overall value. These may seem relatively basic, but these are things that what we say close an operation. It's what validates that operation to be true for all values that fit within that space. In this case, in the previous case, we validated commutative, associative, and identities for normal addition, and therefore addition works for all numbers that are in the real number set, or even the complex number set. However, we needed to show that to be true for the vector set, which is a set of 2 values at a time, or 3. So with these identities in place, we now know that this is true for all concepts, for all vectors. Okay, now that we know that it's true, now we can use that and we can do some operations like here. We have, using the 2 vectors below, we're going to find U plus V, U minus V, and V minus U. Here, U is this top one, and we can define U as its components. U is going in the X direction by 4 up to the Y direction of 1, so it'll have 4, 1. It should look a lot like coordinate points. And V is defined as it's going down 3. So that would actually be the second coordinate. And then it's going over -2. So -2, -3. Okay, if we add, we do U plus V. What we get are the vectors, or the components added together. So 4 plus -2 will give me +2. And then 1 plus -3 will give me a -2. This would be my addition vector. If I draw that, 2, -2 would go to +2, -2 would go to here. This would be my addition vector. If I do subtraction, if I do U minus V, I get 4 minus negative 2 will give me positive 6. And then 1 minus negative 3 will give me positive 4. So 6, which is way out here, and 4 goes to this point over here. Note that really what I did is I took u, and then I added to that the inverse of v. So notice that v has this magnitude. I put that same magnitude here, just going in the other direction. That's how I get to that point. Likewise, if I do another color, do this blue. If I do v minus u, what should happen is I should go to v, and I should add the opposite of u. So notice that u is this length, but it's going in that direction. So all I need to do is change the direction and have it go that way. So I should get a value that should go down here somewhere. And if we do v minus u, we get negative 2 minus 4 is negative 6, and then negative 3 minus 1 is negative 4. We get the inverse of the previous one. So we get 6, negative 4, so we get to right there, which is what I expected. So those are some examples of adding and subtracting vectors. Now, adding is not the only operation we're going to do. We're also going to do multiplication. However, multiplication is kind of hard to talk about with vectors because there's multiple types of multiplication. The first type of multiplication we're going to talk about is what is called scalar multiplication. When you're multiplying by a scalar, what you're doing is you're scaling the vector that you have, which means that you're either increasing or decreasing in size or magnitude. What that also means is that the direction of the vector is not going to change. Notice that before, when we did addition, we created a new vector that had a different magnitude and a different direction. With scalar multiplication, all we're going to do is either magnify it or minimize it by some scalar value. That means that the thing we're actually multiplying in this case is that we're taking a value c, which is going to be a constant, multiplying by a vector v. And what that actually does is it multiplies each of the components by c itself. These are also pretty easy to confirm with the different properties. For example, commutative property, saying c times v equals v times c. Well, c times v is c times v1, v2. V times c is v1, v2 times c. That is still going to result in the same thing overall. This one's going to give you cv1, cv2. This one's going to give you really v1c, v2c. By the commutative property of multiplication, we know these are the same thing, so that's validated. We also have the same true for the commutative property. The commutative property we have, particularly for different constants, if you have c, let's say c times v, and then we'll add another constant in there, d. So I'll say d is also a real number. That should be the same as c times v times d. And we should find that result pretty easily. This one, c times v, we know will give you cv1, cv2 times d. Actually, I'm going to try to not even write that dot. So cv and d and c and vd. And this should equal, on this side, c times the vector dv1 and dv2. And then we just have to multiply d in on the left side here, c in on the right side, and we get the exact same thing. We get c dv1, c dv2 equals c dv1, c dv2. Done. Lastly, for the identity, we just need a number such that if we operate with that, it doesn't change the value. So some number operated with v such that we get the vector v back. This one is going to have the same as the multiplication identity, which is going to be 1. If we do 1 times v, 1 times v gives me 1 times v1, 1 times v2, which is just v1, v2, or v. It doesn't change v at all if you multiply by 1. So therefore, we have a multiplicative identity. Therefore, we should be able to go back. So all of these are still true for scalar multiplication. And graphically, what that looks like, if you have a vector like this, if you multiply that by 2, what you get is a vector that's doubled. So you get this vector instead. Still starting at the same location, still going in the same direction. It's just increase or decrease in size or magnitude. With both of those in mind, we can actually talk about how to calculate magnitude and direction then for any given vector. Which really we've honestly done before, because any vector we have should form a triangle, like what I have here. If we indicate this vector in black, I would say that the magnitude, which we typically indicate with double bar V, that's how we usually do magnitude. I will say that the book sometimes does this. However, I like to shy away from that because that looks too much like absolute value of V. So double bar for when I write that means that magnitude. The magnitude of V, which is the length of this really, I should be able to find when thinking about how much I change vertically versus how much I change horizontally. And that's relatively simple. We have that for any given vector that's defined as such, for v1 and v2, we can instead say that the x and y coordinates can be defined by the magnitude times cosine and the magnitude times sine, which is what we know from trigonometry. We know that cosine is defined as the adjacent over the hypotenuse, and sine is defined as the hypotenuse over the adjacent, or the opposite over the hypotenuse. And then if we solve for v1 and v2, we get those two components here. We get absolute, see exactly why I don't like absolute value. Magnitude times cosine and the magnitude times sine. Which, thinking about scalar multiplication, since they're both multiplied by the same thing on the inside, I should be able to pull that magnitude outside as a scalar. And I should now be able to define each of those. The scalar itself, the magnitude, I should be able to find by taking square root of v1 squared plus v2 squared, which is the Pythagorean theorem, hence the triangle. And I should also be able to find theta by taking inverse of v2, the opposite, over the adjacent v1. So finding the magnitude and the direction it's really just polar. It's the same thing. They're using the same concepts as polar, which is why they will very often agree with each other and will go back and forth nicely. Now there are other ways of finding the direction, the angle. There's many, many different ways of finding that. It's not just the one. You don't only have to use tangent. For example, since we defined that v1 over the magnitude equals cosine of theta, we should be able to find theta by simply taking cosine inverse of both sides. So if you have the first component in the magnitude, you should be able to divide those, take cosine inverse, and you should get your angle measure. Same concept. The only thing you're going to have to keep in mind with finding the direction is that when you take the inverse functions, so tan inverse, cosine inverse, sine inverse, they're all restricted in terms of their range, the range of values that they will produce. So you do need to keep in mind the components themselves of what quadrant you should be in. For example, tan inverse will only ever give you angle measures that fall within quadrant 1 and quadrant 4. So if your components lead to a vector that should fall in quadrant 3, you should know that you need to adjust your angle measure you get from tan inverse appropriately to get that new angle. Okay. So a lot of this is trig. This is just your basic trig, just with magnitude of v instead of hypotenuse. Same thing. Let's do a couple of applied examples of this. First, I have an example that has to do with bearing. We have a ferry in Burlington, Vermont that often takes people across Lake Champlain in Plattsburgh, New York. A ferry travels at about 25 miles per hour north 30 degrees west from Burlington to Plattsburgh against a current in the lake that travels about 5 miles south 50 degrees west. We want to find the true speed and bearing of the ferry. Okay, now first, what each of these mean. Bearing is an angle measure that is relating to your first direction. So north and south is usually how we indicate bearing. And then it'll give you an angle measure that comes off of that direction in either the direction of either east or west. So when you think of bearing here, you really want to think about north and south particularly. North 30 degrees west means start north and then go 30 degrees in the direction of west. This right here I'll put in blue. That is my ferry. So this I'll say is F. However, I also have a current. The current is going south 50 degrees west. So go south first, and then turn 50 degrees in the west direction. So that would maybe be this way. So maybe something like that. This would be my current. $50. What we want to find is a true speed and bearing of the ferry, which is going to be the addition of these. If you combine both the vector that defines the ferry and also the vector that defines the current going against the ferry, I should be able to add those together and come up with a new bearing that comes out from this, which maybe I'll put in red. So I want to find the red one. To do so, let's label some concepts that we have about both the ferry and the current. For the ferry, we know the absolute value, or not the absolute value, we know the magnitude of the ferry, because the ferry is going 25 miles per hour. So we can say the magnitude of it is 25, compared to the magnitude of the current, which it says is going 5 miles per hour. So 5. We also know the angle measure for the ferry. It's north 30 degrees west, which, if I think of from the standard position, is 90 plus 30 gives you 120 degrees. Whereas the angle measure for the current, this is below the negative x-axis, so that means it's more than 180 degrees in that direction. So 180 plus the remainder here would be another 40. That should give me 220 degrees. Or if you want to consider it negative, you could also consider this as negative 140 degrees. That would also work. Because that would be going back 140 degrees. Okay. If we combine these together, we should hopefully be able to find that red vector there. I'll use positive 220 because I think it's a little bit easier. Okay. Now, the vectors themselves, the ferry vector then, is going to be defined by the magnitude times the cosine and sine of that angle measure. So we should be able to say 25 times cosine of 120 and sine of 120. That'll give us 25. I'll move on the inside. Cosine of 120 degrees. That's the same as 2 pi over 3, which cosine of that is 1/2. So on the inside, we're going to have 25 times 1/2, or 25 over 2. And then for sine of 120, that will give you root 3 over 2. So you'll have 25 root 3 divided by 2. And then for the current, we have 5 times cosine of 220 and sine of 220. Oh, one of these actually should be negative. This should be negative 25 over 2. Okay. Cosine of 220, that's in quadrant 3, so it'll be negative as well. But that's going to be root 3 over 2. So we'll have negative 5 root 3 over 2. Followed by sine of 220, which is 1/2 negative, so negative 5 over 2. With all that in mind, we now should be able to find f plus c, the addition of these two vectors. So f plus c should equal the addition of these two, should equal negative 25 over 2 minus 5 root 3 over 2. So I'll say negative 25 minus 5 root 3 all over 2. And then for the second one, we have 25 root 3 minus 5 all over 2. So that would be my new vector for the bearing, or for the new ferry, considering the current. But we want to find the speed and the bearing of the ferry, which means that we want to find both the magnitude and also the angle measure for this. So if we want to find the magnitude of f plus c, what we want to do is the square root of each of these terms, negative 25 minus 5 root 3 over 2 squared, and then the other term, 25 root 3 minus 5 over 2 quantity squared. Oh, hold on. We actually can't do cosine of 220. It's not a nice number, so both of those are off. F plus c is actually going to be negative 25 over 2 plus 5 cosine of 220, which is negative. And then the other one's going to be 25 root 3 over 2 plus 5 sine of 220. So then we find our magnitude then. Let's write this out better. By doing negative 25 over 2 plus 5 cosine of 220 quantity squared. And then also on the inside we also have 25 root 3 over 2 plus 5 sine of 220 quantity squared, all on the inside of that square root. Okay. That we can approximate. We can say that's approximately 24-ish, 0.629 if you calculate that. Then you can also find the direction, theta, in a few different ways. You can either take your magnitude now and then divide that away from the first component and take cosine inverse, or you can use tangent using the original values, particularly if you're not sure if you did the magnitude right. So we can do the fraction of my original two values of v2 over v1. So v2 being the 25 root 3 over 2 plus 5 sine of 220. And then the other one being negative 25 over 2 plus 5 cosine of 220. If you calculate both of these, what you get is about negative 48.46. I'll just say negative 48. However, we identified that as wrong because negative 48 is in quadrant 1. As I said with tangent, tangent is only defined, or tan inverse anyway, is only defined within quadrant 1 and 4. Tan inverse of this stuff is only defined in quadrant 1 and 4. So we need to add 180 degrees to get to the correct value. So that plus 180 should give you positive 132. Or in terms of bearing, that'll be north 42 degrees west. So those will be our two values. The speed, 24.629 miles per hour, and the bearing, north 42 degrees west. Okay. You could just get 42 by taking 90 away. That way you only have the angle measure that's in quadrant 2. All right, sorry about that hiccup earlier, but that should fix up everything for that problem. Let's do another one. Let's do one that has to do with forces, or more forces anyway. A sign weighing 20 pounds is hung on the ceiling with 2 wires of different tension, represented by the free body diagram below. The angle measure formed by T1 at the ceiling is 50 degrees, so that means that this angle right here is 50 degrees. And the angle measure formed by T2 in the ceiling is 35 degrees, so this one here is 35. We want to find the magnitude of tension force of each wire. Okay. Well, to do that, since we have a free body diagram, we want to find a point where we can consider all the forces being in their normal position. And if we do that right here, that means I have one force for this tension, I have one force for this tension, and I have one force for the weight of the sign as well. And they're all coming away from this normalized position. Then from there, I have the x-axis, the y-axis, the x-axis, and all I need to do is consider what these actual vectors look like. All right, for T1, T1 has a magnitude that is unknown. We do not know what that is. That's kind of the question here. But we do know the direction. We know the direction of T1 is 50 degrees is this angle measure here, which means by the vertical angle theorem, this is 50 degrees. So then from the standard position, this is 130 degrees. So it's a 130 degree angle measure. And so we should be able to at least write down T1 as the vector of, we can even pull out T1 if you want to, or put it in. We can put the magnitude of T1 times cosine of 130, and then the magnitude of T1 times sine of 130. That would be the first vector. T2 also has an unknown magnitude. We're going to find that. But the angle measure of T2 is a little bit easier. T2 has a 35 degree angle measure there. So maybe I'll put that in another color. Let's say green. So this we defined as a 35 degree angle measure, which means by the vertical angle theorem, this is 35. And that's the only angle measure I need. So then T2 is going to be the magnitude of T2 times cosine of 35, and then the magnitude of T2 times sine of 35. The only one we have left is the weight. The weight is a lot easier because we know both things. We know both the magnitude and the direction. The magnitude of that is 20 pounds. We're going to find the magnitude of both T1 and T2 that should support that 20-pound sign. So if I even write those down slowly, the magnitude of W is 20 pounds. And the angle measure for W, in this case, if you swing that all the way around, that is 270 degrees, or 3 pi over 2. So then W we can define as 20 times cosine of 270 and 20 times sine of 270. And cosine of 270 is 1, or 0 rather. So that'll give you 0. And 20 times sine of 270, sine of 270 is negative 1, so you get negative 20. And with that, we have all three of the vectors we need. W, T1, and T2. Those are all the forces acting upon the system. Now, because the sign isn't moving at all, the system is it is in equilibrium. We likewise should be able to take all three of these vectors together. T1 plus T2 plus W. All three of these vectors should equal the 0 vector. Because If I put all these vectors together, there's no movement. There is no direction, there's no travel, there's no distance. Nothing's happening. That sign is staying where it is. So there's no motion here. So that's all the setup we need. Now we can work on finding this. If we do t1 plus t2 plus w, we can do a couple things. We can actually move w to the other side if you want, or we can keep it here. I'd say move w to the other side. So t1 plus t2 equals negative w, which is just going to end up being 0 and positive 20. So then, if we take what t1 and t2 are, we have the addition of those to be the magnitude of t1 times cosine of 130 plus the magnitude of t2 plus cosine of 35. And then for the second component, we have magnitude of t2 times cosine of, or sine of 130 plus magnitude of t2 plus sine of 35 equals 0 and 20. And now we could set up a system of equations. The first component equal to the other first component. So magnitude of t1 cosine of 130 plus magnitude of t2 cosine of 35 equal to 0. And we also have the magnitude of t1 sine of 130 plus magnitude of t2 sine of 35 equals positive 20. Since we have a system of equations, sine of 130, cosine of 130, cosine of 35, sine of 35, those are all just constants. We have a system of equations of two variables. You can even consider this x and y. Then all we need to do is solve for one variable and plug into the other, particularly with the first equation equaling 0. We can solve for either one. I'll solve for t1, and you should get magnitude of t1. Yeah, put that down here. Magnitude of t1 is equal to, subtract this to the other side to get negative magnitude of t2, cosine of 35, divide cosine of 130 to the other side, and you get an equation for t1. Then, if you plug that into t1 for the second equation, you get negative magnitude of t2, cosine of 35 over cosine of 130, times sine of 130 plus magnitude of t2 sine of 35 equals 20. I just plugged this stuff into t1. Now solving for t2 just takes a little bit of algebra. We can factor t2 out of the whole thing and then move things over. First, I would subtract the sine of 35 over, so I'd have 20 minus sine of 35. Oh, not subtract sine of 35. What am I doing? I would divide everything else over. So I'd actually end up having t2 equals 20 divided by all of this, which in this case is going to be negative cosine 35 over cosine of 130 times sine of 130 plus sine of 35. The bottom will give you about 1.55-ish, and when you divide that away from 20, you get that the magnitude of t2 is equal to about 12.905. And that'll be a number of pounds. So we have the magnitude of t2. We also need the magnitude of t1. And since we already have this equation right here, why not just plug in magnitude of t2? So then magnitude of t1 equals negative 12.905 times cosine of 35 over cosine of 130. And you get negative 12.905 times cosine of 35. Then you divide that by cosine of 130. Cosine of 130 will be negative, which will cancel out the top negative. And you get approximately 16.446 pounds. All right, so those are the two different tensions. Note that they do add up to more than 20. That is kind of expected because the weight is being split among both of them. They don't both take 20, but they do take a little bit more because they're taking the weights at different angles. All right, so those are a couple examples of using vectors, setting up vectors, and doing some addition multiplication. Lastly, we also have the concept of unit vectors. We basically already have talked about unit vectors when we talked about taking the magnitude of v out of the previous vector. This concept here. When we took the magnitude of v out, we were left with cosine and sine, which are going to define a point x and y on the unit circle. The unit circle has a radius of 1. That is what we mean by a unit vector. If the magnitude or radius of the vector itself is 1, that is a singular unit. In order to find a unit vector very easily, just take the vector you have, divide by its magnitude, and you get its unit vector. It'll be the same vector, or the vector in the same direction, but with a different magnitude. That magnitude being 1. You can also decompose or take apart a vector into what we call principal unit vectors, which are just vectors that go down principal axes. So, for example, I is one of the unit vectors, and that vector is defined as 1, 0. So it only incorporates the x coordinates. Whereas k is another one, and that should be k equals 0 and 1, because it only involves the y piece of it. All right. Actually, j should be, yeah. J should be for the y-axis. So j equals 0, 1. Yeah. I, j, k in alphabetical order, just like x, y, z. You can decompose any vector very simply by taking its components and multiplying that by unit vectors. v1 times I and v2 times j will result in the same exact vector. If you have v1 times I plus v2 times j, where I is 1, 0, and j is 0, 1, then you get v1, 0 plus 0 v2, which is just v1, v2, or the original vector v. This is another common way of just representing vectors, is in its decomposition form instead. And some people like this because it looks more algebraic in nature, particularly when you treat I and j as different variables. You only really need to do is deal with the coefficients in front of it, and you would add and subtract like coefficients similarly. Likewise, the addition and scalar multiplication operations still apply, and I already have those summed here. V plus or minus w doesn't really matter, will result simply in the components being added for I and the components being added for j as coefficients. Likewise, if you multiply by a scalar k or c, whatever, then all you're doing is multiplying the coefficients on I and j by that scalar. So let's just do a quick example of that then. We're going to find a plus b for a plus 2b, the magnitude of a and the magnitude of a minus b for the vectors a equals 2i plus 4j, b equals 3i plus j. Okay, relatively simple. All we need to do is combine these appropriately. So a plus b, we have a is 2i and negative 3i, so we're going to combine those together, and we get minus i left. And then 4j plus j will give us plus 5j. Nice. The next one asks for 4a plus 2b. All right, well, 4a is going to be 2i plus 4j times 4, which is going to be 8i plus 16j. And then 2b is going to be negative 6i plus 2j. That will give us 8i minus 6i will give us 2i. 16j plus 2j will give us 18j. That's 2 of those done. How about the magnitude of a? The magnitude of a is the magnitude of 2i plus 4j. If you want, you can change this into 2 comma 4 and work with it that way. However, remember this is just going to be the Pythagorean theorem. So the square root of 2 squared plus 4 squared. That'll give us 4 plus 16. That'll give us 20. Or 2 root 5. That'd be the magnitude of a. And lastly, we want the magnitude of a minus b, that vector. So first we need to find the vector of a minus b. That'll be 2i minus a negative 3i will give us 5i. Plus 4j minus j will give us 3j. So then the magnitude of a minus b would be the square root of 5 squared plus 3 squared. It's 25 plus 9, that's 34, which doesn't simplify any further. So root 34. And that's it. Okay, so that's quite a few examples of dealing with vectors and some more complicated examples of those. If you have any questions, feel free to put those in the comments below, or you can ask your instructor directly. With that said, I hope you have a nice day.